Hi, this lecture is going to be on amides, next two lectures, and this is going to be the last acid derivatives that we're going to be talking about. Remember way back when we started talking about acid derivatives, we looked at the functional groups and what they look like. So your first goal for this lecture is, given a structure, to be able to recognize the amide functional group. So here's a structure of penicillin, which is a compound that we're going to be talking about later on. You should be able to right away recognize the functional groups that are present in this molecule. That is, you see a carboxylic acid here. And notice the C-double NH. So that's an amide functional group. And there's actually another amide functional group, which is C-double-N in a cyclic form. All right. So this is a regular amide. This, whenever you see an amide in a cyclic structure, they're called lactams. All right. So whether or not, either way, you should be able to recognize the amide functional group. Now, amides are one of the more important functional groups of the acid derivatives. So we just went over a couple lectures on ester, and amides are also very prevalent in nature. They're the most abundant bonds that you'll find in proteins. So the amide bonds are found in proteins. And we'll take a look at this in Unit 4, actually Unit 5. When we go over biochemistry stuff, we're going to look at lipids and proteins. And you'll see later on that between the amino acids, so I'm going to abbreviate amino acids as AA, then when you form the polymer, which is what we call protein, the bonds that connect the amino acid together are amide bonds. So amide bonds are prevalent in nature. And you'll see we're going to go over polyamides. So these are, if you will, synthetic, man-made polymer, and those polyamides would be linked each monomeric unit by an amide bond as well. All right, so amides are very important, so it's important for us to be able to name them and then also understand the characteristic of amide bonds as well. So we'll go over that next. So let's start out with the nomenclature, and the nomenclature is simple, just like other acid derivatives. So you're going to drop the ic acid or the oic acid from the parent carboxylic acid, and you're going to change that to amide. Now, some of the amide groups are going to be unfunctionalized on the nitrogen. In other words, there's no R groups on the nitrogen. That you just name it as an amide and you're done. If on the nitrogen you have R groups, it could be same or different, then you name each of the alkyl substituents on the nitrogen, and you use the capital N, not a small n, capital N, to determine, to indicate that the R group that you're naming is on the nitrogen. All right, so let's do a few examples. We'll start out with doing the simple one, and so take a look at that structure and ask yourself, what would be the parent carboxylic acid? All right, so if this was OH here, you would name this 1, 2, 3, 4, 5. 5 carbon is the longest. So some kind of pentanoic acid if there was no double bond here, but there is double bond here, so it would be pentenoic acid. But because this is not an OH but an NH2, you drop the oic acid and add the amide. So pentenamide would be the parent name. And this is going to be understood always to be carbon 1 because it's going to be at the end with a high ranking. So you have to say where the double bond is for the ene, so that would be 3 pentenamide. And then any other substituents you have, which in this case is 3-chloral, 3-pentenamide, it would be the name of that. Now notice this structure is exactly the same as this, except for the fact that you have 2 ethyl groups. So the name of this would be N, because there's 2 of them, N. So N, comma, N. Notice they're both capitalized because you've used little n, then that means you are indicating like N-butane, like normal. That's what the little n would be. So capitalize N, comma, N for the 2 ethyl groups, and it will be diethyl. And then this whole thing, 3-chloral, 3-pentenamide would be the name. So notice this addition to the parent name. All right. So if the R group is different, let's say one was methyl and one was ethyl, then you would put it in alphabetical order. So it would be N-ethyl, and then dash N-methyl, and then 3-chloral, 3-pentenamide. All right. So if you were given a name N,N-diphenylbenzamide, then you should be able to also draw that. So you go back to the end of the name that tells you what kind of functional group you have. So you know that you have an amide. So you have some kind of C-O and then N attached to it. That's what's indicated to you by amide. So if it was, the root name is from benz, so this is carboxylic acid derivative from benzoic acid. So you know that benzoic acid is the one with benzene group attached to it, so that would be the benzamide. So you would just put NH2 if this wasn't present, N,N-diphenyl. So on the nitrogen we have 2 phenyl groups, so that's, and then the benzamide is indicated by here. So that will be the structure of that compound. All right, so hopefully you should be able to do naming problems as shown here, 21.12BD and 21.13C. And then we'll move on to the characteristics of amide bonds next. All right, so this NMR structure has got to do with this question of basicity of amides versus amines. All right, so a lot of students get confused, amides versus amines, and we're going to have a separate lecture on amines, and there's a separate chapter in your book about it. So those are 2 very different functional groups. So amides are, for example, the nitrogen is bonded directly to C-O, and this could have an R group or an H, but then amines are just nitrogen groups attached to R groups. All right, so here's an example of an amine. It's got amine nitrogen group directly attached to methyl group in this case, but any R group attached to nitrogen will be classified as amines. All right. So if you recall from before, you've seen this kind of, this is in the next page, this kind of diagram before, in which the acid chloride is the most reactive, followed by anhydride, followed by ester, and then followed by amides. So amides are the least reactive out of all of the acid derivatives, and we want to go over why that is the case. And that kind of explains its characteristics in how it reacts in a chemical reaction. All right, so this has got a lot to do, its reactivity's got a lot to do with what is happening with this lone pair in the amide versus amine, all right? And if you understand that, that also will explain why amide is the most stable of the functional groups, all right? So notice that this nitrogen lone pair could be contributing toward the C-double-O, and we talked about this before. So this NMR right here is in fact NMR of DMF, is dimethylformamide, which has a structure of dimethyl. In fact, you should be able to draw that dimethyl formamide. So this is the formic acid derivative, and so this is often used as a solvent. And if you take an NMR of this molecule, you see the aldehyde peak around 8 ppm. And you might think that these two methyl groups should be equivalent if this bond is freely rotating, right? If it's freely rotating, this methyl and this methyl should not be distinguishable, all right? And so it should show up as a singlet worth 6 hydrogens in a proton NMR. But that's not the case, as you could see here. Notice the doublet here. It looks like a doublet, but they're actually referring to a singlet for this methyl and a singlet for this methyl. In other words, they are showing up as two different methyl groups. And the reason for that is because of this resonance structure that we talked about, in which there's a strong, the single bonded here, characteristics of double bond between the carbon and nitrogen, all right? So because of this double bond character, this methyl group and this methyl group are showing up as two different methyl groups because they're not freely rotating about the CN bond, all right? So it's almost like looking at an alkene in a way. This methyl group is cis to O minus, but this methyl group is cis to hydrogen. So they're going to have slightly different environment, right? And so there's a barrier to rotation causing these two methyl groups to be different. And if you look at the bond length of this CN bond of here is 1.32 angstroms, all right? Whereas, so if you compare this CN single bond to a CC normal double bond, that's 1.34 angstroms. Whereas a CC single bond is about 1.5 angstroms. So notice the CN bond, right, of the amide is a lot shorter than a normal single bond. In fact, it's a lot closer to a double bond than a single bond. So that's all these things are telling us that there's a lot of double bond character, and is proven by the proton NMR of the DMF, all right? So what does that mean in terms of reactivity? That means that the lone pair on the amide is not as available as the lone pair on the nitrogen. So what that means is, the consequence of this is that this amine, so this is amine, it's going to be a lot more basic. In other words, it's going to be able to go grab a proton a lot more readily, and which means that it's also going to be a lot more nucleophilic. So it's able to go and react as a nucleophile at an electrophilic center. So don't get these two different functional groups mixed up, because they're very, very different, and their reactivity is very different. And we'll continue this in the next lecture.